Welcome to Science Snippets Fun Facts and Trivia. Today, we bring you, does gravity really exist? The truth modern physics is questioning. Gravity is one of the most familiar forces in our everyday lives. When we drop an object, it falls to the ground. If we throw a ball into the air, it eventually comes back down. This force, known as gravity, is often taken for granted. But in reality, its true nature remains one of the most profound mysteries in science. So, what exactly is gravity? Gravity is the force by which two objects are drawn to each other. Just as Earth pulls us down, we also, in an incredibly small way, exert a pull on Earth. The story of our understanding of gravity goes back to the 17th century and is forever linked to the scientist Isaac Newton. Legend has it that he was inspired to investigate gravity when he saw an apple fall from a tree. This simple observation sparked his curiosity: why do objects fall downwards? Newton's answer to this question was the law of universal gravitation. He proposed that every object in the universe attracts every other object with a force proportional to their masses, and inversely proportional to the square of the distance between them. This became the basis of Newtonian physics, and helped scientists understand the motion of objects, from planets to pebbles. According to Newton, this universal gravitational force is what keeps the Moon in orbit around Earth and binds our entire solar system together. His theory revolutionized science, creating a framework that worked well for both terrestrial and celestial bodies. However, Newton's theory couldn't fully explain certain phenomena. Why do objects of different masses fall at the same rate when dropped? What actually causes gravity? For centuries, scientists searched for answers. But it wasn't until the early 20th century that a new understanding began to emerge. Albert Einstein, with his theory of general relativity, provided a radically different picture of gravity. Rather than a force acting at a distance, he described gravity as the curvature of spacetime caused by mass and energy. In Einstein's view, Earth's mass bends the fabric of spacetime, causing objects to fall toward it. In this framework, gravity isn't a force at all, but rather an effect of curved spacetime. This idea marked a turning point in physics. Einstein's theory was confirmed through astronomical observations, such as the bending of starlight around massive objects, a phenomenon known as gravitational lensing. It expanded our understanding of the universe, allowing us to predict the behavior of objects in extreme gravitational fields, like those near black holes. But even Einstein's elegant model of curved spacetime hasn't answered all our questions. Gravity remains unique in that, unlike the other fundamental forces, it doesn't seem to fit with quantum mechanics, which governs the subatomic world. Despite our advancements, gravity is still enigmatic. From Newton's apple to Einstein's spacetime, we've come a long way, yet we continue to seek a deeper understanding. Could it be that gravity, as we know it, is only part of the story? Some physicists now question whether gravity itself even truly exists in the way we understand it. And that brings us to one of the biggest questions facing modern physics. What is gravity really? Gravity as we know it has been defined by two of the most influential theories in the history of science: Newton's law of universal gravitation and Einstein's theory of general relativity. These two theories, though addressing the same force, offer vastly different perspectives on how gravity operates. Isaac Newton's approach to gravity was groundbreaking for his time. In the late 17th century, Newton proposed that gravity is a force that acts at a distance, pulling objects together in direct proportion to their masses. and inversely proportional to the square of the distance between them. This formula, known as the inverse square law, meant that the gravitational force between two objects would weaken the further apart they were. Newton's law could explain why planets orbit the sun, and why objects fall to the ground when dropped. His discovery created a foundation for what we now call classical mechanics, and laid the groundwork for centuries of scientific exploration. But Newton's theory had some unresolved issues. For instance, he couldn't explain how gravity worked over a distance. Why would the Earth's mass attract the Moon, even though there was a vast amount of empty space between them? Newton famously admitted he had no hypothesis for this mysterious force at a distance. This puzzling gap in understanding would remain for centuries. Enter Albert Einstein, who in 1915 presented a completely new understanding of gravity. Einstein's theory of general relativity proposed that gravity is not a force between objects, as Newton suggested, but rather a warping of spacetime caused by mass and energy. Imagine placing a heavy ball on a stretched rubber sheet. The weight causes the sheet to bend. Now, if you roll a smaller ball near this depression, it will spiral inward, pulled by the curvature of the sheet. Similarly, in Einstein's universe, massive objects like the Sun create curves in spacetime, and other objects follow those curves, giving the appearance of a gravitational pull. Einstein's theory was revolutionary, and its predictions were confirmed by several key experiments. One of the most famous tests occurred in 1919, when astronomers observed starlight bending around the Sun during a solar eclipse, just as Einstein had predicted. This phenomenon, known as gravitational lensing, was impossible to explain with Newtonian gravity. Einstein's theory not only explained gravitational attraction, but also predicted extreme phenomena, such as black hole objects so dense that their gravitational pull warps spacetime itself and allows no light to escape. While Einstein's theory has passed every observational test to date, it also introduces a unique paradox. It doesn't fully align with quantum mechanics. Quantum mechanics, the theory that governs the behavior of particles at the smallest scales, has its own set of rules that seem incompatible with general relativity. Physicists have been struggling to reconcile these two frameworks, which is why we still don't have a complete theory of everything that can explain all aspects of gravity. So, from Newton's invisible force pulling apples to the ground, to Einstein's curved spacetime guiding planets around stars, our understanding of gravity has evolved dramatically. Yet, questions linger. Why does gravity behave so differently from the other fundamental forces? And how can we reconcile it with the strange, probabilistic world of quantum mechanics? In seeking these answers, modern physicists have started to question the very nature of gravity itself. Could it be that our understanding of gravity is flawed, or even incomplete? As we'll see next, some scientists believe that gravity might not even exist in the way we imagine. Instead, it may be a byproduct of deeper, more fundamental laws of the universe. It might seem impossible to imagine a universe without gravity. After all, gravity is fundamental to our understanding of how the universe works. But in recent years, some radical ideas in physics suggest that gravity might not be what we think it is. Could it be possible that gravity, as we know it, doesn't actually exist? This provocative question is leading scientists down some surprising paths. One of the most intriguing ideas comes from a hypothesis called entropic gravity, proposed by Dutch theoretical physicist Eric Verlinde. According to this theory, gravity isn't a fundamental force at all. Instead, It's a kind of byproduct of something deeper, a concept related to thermodynamics and entropy. Entropy is the measure of disorder within a system, and thermodynamics is the study of how energy flows and changes within physical systems. Verlind suggests that gravity emerges naturally from the tendency of systems to increase in entropy. Imagine, for instance, a room filled with particles moving around at random. Over time, these particles will spread out, filling the room evenly, because this is the most disordered or highest entropy arrangement. Verlind's idea is that the same basic principle could apply to gravity. In this view, objects don't attract each other through a mysterious force. Instead, they naturally move in ways that maximize entropy, which gives the appearance of a gravitational pull. While it's a highly theoretical approach, entropic gravity could potentially explain certain phenomena that traditional gravity theories struggle with, especially at the cosmic scale. Some scientists are hopeful that this idea might help solve one of the biggest mysteries in modern physics: dark matter. Dark matter is an invisible substance that seems to account for most of the matter in the universe. Traditional gravity models predict certain behaviors in galaxies and galaxy clusters that can only be explained if we assume this extra dark matter exists. But what if dark matter is just a placeholder for the effects of entropic gravity? Another radical approach comes from the field of holographic theory. This theory, inspired by discoveries in black hole physics, suggests that our three-dimensional universe may be something like a hologram, with the real information about our universe existing on a two-dimensional surface. According to this concept, gravity, and even the fabric of space itself, could be an illusion, created by information encoded on this distant two-dimensional boundary. The holographic theory has led physicists to reconsider gravity in entirely new ways. If our reality is, in some sense, a projection, then what we perceive as gravity might just be a side effect of deeper physical processes. This idea sounds like science fiction, but it's grounded in advanced physics. In fact, calculations based on holographic principles have been used successfully to explain certain quantum phenomena that would otherwise defy explanation. Finally, quantum gravity theories attempt to bridge the gap between gravity and quantum mechanics by suggesting that gravity might emerge from the same fundamental building blocks that govern particles at the quantum level, in one of the most speculative approaches, called quantum loop gravity. Researchers propose that spacetime itself is made up of tiny, discrete loops. In this view, gravity isn't a force or a warping of continuous spacetime. It's the result of interactions between these microscopic loops of quantum space. These new theories are bold, and none of them have yet been proven. But as our instruments and mathematical models improve, physicists are able to test these ideas in more sophisticated ways. It's possible that one day, we'll uncover the true nature of gravity and find that it's even stranger than we imagine. So, could gravity truly not exist in the way we think? These new theories invite us to keep questioning the fundamental nature of reality. And while no definitive answers exist yet, these radical ideas open the door to new possibilities that could reshape our understanding of the universe. The idea that gravity might be an illusion sounds outlandish, but this hypothesis is gaining traction among some scientists and theorists today. This concept challenges our fundamental understanding, suggesting that gravity isn't a force at all, but a byproduct of deeper, underlying laws of the universe. So, where does this bold hypothesis come from, and what evidence supports it? One of the most influential voices behind This idea is Dutch theoretical physicist Erik Verlinde. In 2011, Verlinde proposed an idea called entropic gravity. According to his theory, gravity is not a fundamental force in the universe, but rather an emergent phenomenon. To understand this, consider how temperature works. It's not a fundamental force, but rather an effect caused by the movement of particles. Verlinde suggests that gravity, like temperature, may be an emergent result of microscopic processes happening at a deeper level. In Verlinde's view, gravity emerges due to entropy, which is a measure of disorder or randomness in a system. According to the laws of thermodynamics, systems naturally evolve toward states of higher entropy. Verlinde proposes that the universe has an inherent tendency to maximize entropy, and that gravity is essentially an effect of this universal drive. To illustrate, imagine a room full of particles bouncing around. Over time, these particles will spread out to fill the space evenly, simply because this is the most disordered or highest entropy arrangement. Similarly, Verlinde's theory suggests that objects move toward each other, not because of a force pulling them together, but because this movement maximizes entropy. The force we interpret as gravity is simply an effect of particles seeking the highest possible entropy state. This theory has several implications. For one, it might offer an explanation for dark matter. Traditional physics suggests that an invisible form of matter, called dark matter, provides the additional gravitational pull needed to hold galaxies together. Yet, despite decades of research, scientists have been unable to directly detect dark matter. Entropic gravity, however, could explain this mystery without invoking any invisible particles. If gravity is an emergent property, then the discrepancies we observe in galaxies could be the result of this entropic effect, rather than any invisible matter. Verlinde's ideas aren't universally accepted, but they've sparked a lot of debate. His theory provides an alternative framework that doesn't rely on the existence of invisible forces or particles, challenging long-standing beliefs in physics. Although entropic gravity is still in its early stages and needs more empirical support, it has the potential to radically shift our understanding of gravity. As physicists continue to explore these ideas, they're finding other potential frameworks that similarly challenge the traditional view of gravity. These theories encourage us to consider that what we experience as gravity might just be a secondary effect of more complex, foundational laws of the universe. If this is true, it may mean that gravity, as we understand it today, is only the tip of the iceberg, a visible effect of hidden mechanisms we're only beginning to uncover. Could the nature of gravity be tied to something as unexpected as entropy, or even a holographic model of the universe? While it might sound like science fiction, these theories offer intriguing alternative perspectives on gravity, each challenging traditional views and suggesting that gravity may be a consequence of deeper laws within the cosmos. One of the foundational ideas behind these theories is the relationship between entropy and gravity. Entropy, as you may know, measures the amount of disorder or randomness in a system. According to the second law of thermodynamics, the entropy of a closed system will naturally increase over time, tending toward maximum disorder. In recent years, some theorists have proposed that gravity itself might arise as a result of this natural tendency for systems to increase their entropy. To understand this, let's revisit the concept of entropic gravity, as developed by physicist Erik Verlinde. Verlinde's theory suggests that objects don't attract each other through a gravitational force in the way we traditionally think. Instead, their motion is driven by the universe's tendency to maximize entropy. According to this view, objects move in ways that maximize disorder, creating the illusion of a gravitational pull between them. This perspective is radical, because it proposes that gravity isn't a standalone force, but an emergent property of thermodynamic processes at a microscopic level. Another theory that has gained attention is the holographic principle, which comes from string theory and black hole physics. The holographic principle suggests that our three-dimensional universe could be a kind of projection, or hologram of information stored on a distant, two-dimensional surface. In this model, everything we perceive in 3 dimensions, including gravity, is encoded on this boundary. How does this work? The idea has its roots in the study of black holes. When an object falls into a black hole, it seems to disappear, lost forever to the pull of intense gravity. However, physicists realized that, theoretically, all the information about that object isn't lost. It's stored on the two-dimensional surface of the black hole, known as the event horizon. This concept led scientists to ask, what if the entire universe operates in a similar way, with all information stored on a distant, two-dimensional boundary? In this model, gravity and other physical phenomena in our universe could be reflections of processes occurring on this holographic boundary. If true, the holographic principle suggests that gravity might not exist as a fundamental force in the way we imagine. Instead, it could be a byproduct of information encoded on this two-dimensional surface. Some physicists believe that this approach could help resolve conflicts between general relativity and quantum mechanics, potentially opening doors to a theory of quantum gravity. Both entropic gravity and the holographic principle represent bold ideas that challenge traditional thinking. They ask us to consider that what we experience as gravity may not be an independent force, but rather an effect emerging from deeper principles in the universe. While these ideas are still highly theoretical, ongoing research and advanced technologies are helping physicists explore these concepts in more detail. The implications of these theories are profound. If gravity is indeed an emergent property of entropy or a holographic effect, then our understanding of space, time, and even reality itself may require a complete overhaul. This line of research is still young, but the questions it raises could lead us toward a radically new vision of the universe. While theories like general relativity explain gravity on large cosmic scales, they don't quite work when we zoom in to the subatomic level. Here, gravity becomes one of physics' biggest puzzles, because it doesn't seem to fit with quantum mechanics, the theory that governs particles at the smallest scales. This divide has led scientists to explore the idea that gravity, as we know it, may be connected to or even arise from quantum mechanics itself. Quantum mechanics is a world of uncertainty, where particles exist in multiple states at once, and events don't happen with absolute certainty but with probabilities. This is a stark contrast to general relativity, where gravity operates predictably across the universe. When physicists try to apply quantum principles to gravity, things get complicated fast. For example, if we try to describe a black hole in quantum terms, we encounter contradictions such as the famous information paradox, which suggests that information about particles could be lost inside a black hole. This paradox and others have driven physicists to search for a theory of quantum gravity, a framework that can unify gravity with the principles of quantum mechanics. One of the leading ideas in this area is quantum loop gravity. This theory proposes that spacetime itself might be made up of tiny, discrete loops, much like pixels on a screen. if spacetime isn't continuous but instead composed of these minuscule loops, then gravity could be an effect that arises from the interactions of these quantum loops. In this model, gravity isn't an independent force, but a byproduct of these fundamental structures. Another approach to quantum gravity is string theory, which suggests that particles are not points but tiny, vibrating strings. According to string theory, these vibrating strings give rise to all known particles and forces, including gravity. This theory also requires additional dimensions beyond the four we experience, meaning that gravity might behave differently on scales we can't observe directly. Although string theory remains unproven, it has fueled ongoing efforts to understand gravity on the quantum level. Yet another approach, called quantum entanglement, also offers insights into gravity's quantum nature. In quantum entanglement, particles become linked in such a way that their states remain connected, even across vast distances. Some physicists speculate that this spooky action at a distance, as Einstein called it, could help explain the fundamental connections that give rise to gravity in the universe. If gravity emerges from these quantum interactions, it might be less a force and more a kind of information link between particles, created by entanglement on a universal scale. While these theories are speculative, they are crucial steps in the quest to understand gravity. In the context of quantum mechanics, a complete theory of quantum gravity could redefine our understanding of not only gravity, but also the fundamental building blocks of reality. It's a mystery that continues to inspire physicists worldwide, and as experiments and technology advance, we may get closer to unraveling the true nature of gravity. Gravity's influence extends across the cosmos, playing a crucial role in the formation of galaxies, stars, and even planets. Without gravity, the structures that fill our universe, the stars, planets, and galaxies, wouldn't exist. So how does gravity shape these celestial bodies? In the early universe, shortly after the Big Bang, matter was scattered in a nearly uniform, chaotic state. But tiny variations in density created regions where some particles clumped together more than others. These clumps exerted a slightly stronger gravitational pull, attracting more matter to them. Over billions of years, these dense pockets of matter grew larger, eventually forming massive clouds of gas and dust. Within these vast clouds, gravity continues to work its magic. As gas and dust accumulate, their own gravity pulls them closer together, compressing the material and increasing its density. As the pressure and temperature rise, nuclear fusion ignites, and a new star is born. Stars, then, are the direct result of gravity, compressing matter until it reaches the conditions needed to start nuclear fusion. But gravity doesn't just create stars, it's also the glue that holds galaxies together. In galaxies, stars orbit a central region, often containing a supermassive black hole. This central gravitational force keeps the stars in a stable orbit, preventing them from dispersing into space. For instance, in our Milky Way galaxy, gravity from the central black hole, combined with the mass of billions of stars, binds the galaxy together in a balanced gravitational dance. Yet, there are still puzzles. Observations show that stars in the outer parts of galaxies move faster than they should. If only visible matter were exerting gravitational pull. This unexpected speed has led scientists to hypothesize the existence of dark matter, a mysterious, invisible substance that exerts extra gravitational force, holding galaxies together. Through gravity's intricate influence, the universe organizes itself into galaxies, stars, and planets, transforming clouds of dust and gas into the celestial bodies that fill the night sky. Without gravity's guiding role, the universe would lack the structure that makes it recognizable to us today. Gravity's effects are everywhere in the cosmos, but some gravitational phenomena remain unexplained, pointing to mysteries like dark matter and dark energy. These elusive substances don't emit, absorb, or reflect light, making them invisible to us, yet they seem to play a massive role in shaping the universe. So, what is the link between gravity and these hidden forces? Let's start with dark matter. Observations of galaxies show that stars on their outer edges orbit at unexpectedly high speeds. According to traditional physics, these stars should be flung into space. However, they remain bound to their galaxies, suggesting the presence of an unseen gravitational force. Scientists have hypothesized that this extra gravitational pull comes from dark matter, an invisible form of matter that makes up about 27% of the universe. Although we can't see or detect dark matter directly, its gravitational effects keep galaxies intact, binding stars and gas within them. Dark energy, on the other hand, seems to work in the opposite direction. While gravity pulls matter together, dark energy appears to push the universe apart, accelerating its expansion. This discovery came as a surprise to scientists in the late 1990s, when they observed distant supernovae and realized that the universe's expansion rate is increasing. Currently, dark energy is estimated to make up about 68% of the universe, dwarfing the amount of normal matter and even dark matter. Although we don't fully understand what dark energy is, its effects suggest a cosmic tug-of-war between gravity, which tries to bind the universe together, and dark energy, which drives it apart. This interplay between gravity, dark matter, and dark energy shapes the universe's large-scale structure. Galaxy clusters, for instance, are bound by both normal gravity and the gravitational influence of dark matter, creating massive, stable structures. But on an even larger scale, dark energy's repulsive effect causes these clusters to drift farther apart, accelerating the universe's expansion. Understanding how gravity interacts with dark matter and dark energy could unlock new insights into the universe's ultimate fate. Will gravity eventually overcome dark energy and cause the universe to contract? Or will dark energy continue pushing everything apart indefinitely? These questions drive some of today's most exciting research, promising to reveal more about the unseen forces that shape the cosmos. Few places in the universe reveal the true power of gravity like black holes. These mysterious objects are regions where gravity becomes so intense that not even light can escape. Black holes are fascinating for scientists because they push the known laws of physics to their limits, offering a glimpse into the extremes of gravity and space-time. Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. This collapse squeezes the star's core into an incredibly dense point, called a singularity, where gravity is thought to be infinitely strong. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not light, not particles, not even information can escape the black hole's gravitational pull. The event horizon is like a one-way gate to oblivion. Anything that crosses this boundary is pulled inexorably toward the singularity, where the known laws of physics break down. Einstein's theory of general relativity predicts that, within this singularity, space-time is stretched to an infinite degree, creating a place where time and space, as we understand them, cease to function. But black holes don't just exist in isolation they can also interact with their surroundings. When a black hole pulls in nearby gas, dust, or even entire stars, it heats this material to extreme temperatures, causing it to emit powerful X-rays. Observing these X-rays has helped scientists detect black holes and study their behavior. Even though the black holes themselves remain invisible, black holes also warp spacetime in ways that lead to some of the universe's most extreme phenomena. One such phenomenon is gravitational lensing, where the immense gravity of a black hole bends the path of light around it. This effect allows us to observe objects behind a black hole, as their light is bent around the massive object. In addition, when black holes merge, they produce ripples in spacetime called gravitational waves. First detected in 2015, gravitational waves confirmed one of Einstein's last predictions, revealing that spacetime is not rigid but flexible, capable of being stretched and compressed. These waves open a new window into the universe, allowing us to hear cosmic events involving massive objects like black holes and neutron stars. Black holes are therefore more than just cosmic curiosities. They represent the extremes of gravity and provide crucial insights into the nature of spacetime itself. By studying black holes, scientists hope to answer some of the deepest questions about the universe. From the nature of gravity to the ultimate fate of spacetime, gravitational waves are ripples in spacetime that reveal a new way of understanding the universe. They were first predicted by Albert Einstein over a century ago, as part of his theory of general relativity. But for decades, they remained purely theoretical. However, in 2015, scientists made an incredible breakthrough: the first direct detection of gravitational waves. This discovery changed our understanding of the cosmos and opened a new window for observing some of the universe's most violent and mysterious events. Gravitational waves are created by massive cosmic events. Think of merging black holes or colliding neutron stars. When two massive objects spiral toward each other and collide, their combined gravitational energy distorts spacetime, sending ripples across the universe. These waves stretch and compress the very fabric of space as they travel, carrying information about the events that created them. Detecting these waves was an extraordinary challenge. Since gravitational waves stretch and compress spacetime itself, they pass through everything, making them nearly undetectable. But scientists at the Laser Interferometer Gravitational Wave Observatory LIGO and Virgo collaboration created incredibly sensitive instruments to measure tiny changes in distance, as small as 1,000th the diameter of a proton. In 2015, LIGO's detectors picked up a faint signal gravitational wave from two black holes merging over 1 billion light-years away. This marked the first direct confirmation of Einstein's theory and a new way of observing the cosmos. Gravitational wave astronomy is already revealing unprecedented insights. We've detected black holes and neutron stars merging, events that were previously invisible to us. Gravitational waves provide unique information because they're not affected by matter or light. They travel directly from their source to us, undistorted. This allows scientists to study the universe's most extreme environments in ways previously impossible. As gravitational wave detectors improve, scientists hope to uncover even more cosmic events and perhaps discover entirely new phenomena. The possibilities are vast. We might observe the merging of supermassive black holes, detect waves from the early universe, or even uncover unknown sources of gravitational waves. These ripples in spacetime have already transformed our understanding of the universe and are likely to continue shaping the future of cosmology. Gravity has shaped the universe from its very first moments, guiding its evolution from the Big Bang to the sprawling cosmos we see today. But how did gravity influence the birth of the universe? And how has it helped create the structures we see around us? To understand gravity's role in the early universe, we need to go back about 13.8 billion years to the Big Bang, the event that marks the beginning of time and space as we know it. In the first fractions of a second, the universe expanded at an unimaginable rate in what's known as cosmic inflation. As the universe expanded, it began to cool, allowing particles to form. At this point, gravity started to play a critical role, pulling particles together into denser regions, and setting the stage for the formation of galaxies, stars, and planets. In the early universe, matter was distributed unevenly, with tiny fluctuations in density. These fluctuations are believed to be the seeds of all the cosmic structures we see today. Gravity amplified these slight density variations, drawing particles into clumps and helping matter accumulate. Over billions of years, these clumps grew larger, forming the first galaxies and clusters of galaxies. Without gravity's relentless pull, these structures would have remained scattered, and the universe would look vastly different. Gravity has continued to shape the universe throughout its evolution, creating the stars and galaxies that fill the cosmos. Even now, it acts as a stabilizing force, binding stars within galaxies and galaxies within clusters. But the relationship between gravity and the universe's expansion adds another layer of complexity. Since the late 1990s, scientists have known that the universe's expansion is accelerating, likely due to the influence of dark energy, a mysterious force pushing galaxies apart. This means that gravity and dark energy are in a constant balance, one trying to bind the universe together, the other pushing it apart. Understanding how gravity has shaped the universe from the Big Bang to today helps scientists predict its future. Will gravity's pull eventually overcome dark energy, causing the universe to contract, or will dark energy continue to drive the expansion, leading to a big freeze where galaxies drift apart indefinitely? These questions drive ongoing research, as scientists strive to understand gravity's role not only in the past, but also in the ultimate fate of the cosmos. As radical as it may sound, the idea that gravity could be an illusion challenges some of the most fundamental principles in physics. But if gravity is not a fundamental force, what would that mean for our understanding of the universe and potentially for our future? First, let's revisit what scientists mean when they suggest gravity might be an illusion. In theories like entropic gravity or the holographic principle, gravity isn't a force in the traditional sense, but rather an emergent property that arises from more fundamental processes, such as entropy or the nature of information. In this view, what we experience as gravity could be a byproduct of interactions at a deeper level of reality. If true, this idea could change everything we know about space, time, and the nature of reality. For instance, it may mean that there are hidden layers of reality, or dimensions that interact to create the effects we perceive as gravity. Technologies we currently view as science fiction, like faster than light travel or even manipulating space-time, could one day be feasible if we learn to understand and harness these hidden aspects of nature. It might sound far-fetched, but just as electricity seemed like magic before it was understood, gravity, as an emergent property, could reveal possibilities we can't fully imagine today. On a practical level, this new understanding of gravity could lead to advancements in fields like quantum computing and materials science, If gravity can be explained through quantum mechanics, then devices based on quantum principles may one day be able to manipulate gravity on small scales, potentially leading to breakthroughs in energy or transportation. However, these ideas are still highly speculative and would require breakthroughs in physics, technology, and our understanding of quantum mechanics. The challenges are immense, but so are the possibilities. If gravity is indeed an emergent property, we may be standing at the edge of a new scientific revolution, one that will reshape our understanding of the universe and our place within it. If you found this video helpful or interesting, please give it a thumbs up and subscribe to the channel.